Black holes, one of the most baffling and peculiar phenomena in the universe, remain the focus of intense examination and interest among experts in space and physicists in general. These heavenly objects, whose monstrous nature defines their gravitational pull and the total absence of light emission, represent a limit beyond which the known laws of physical science are no longer relevant. First speculated in 1916 by Albert Einstein as a direct result of his theory of physics. Black holes were only conceptual until technological advances made their indirect detection possible in the 20th century. In the 1960s, a turning point occurred when scientists studying the Cygnus constellation stars came across an unusual discovery by accident: a celestial object, a brilliant blue star emitting high-energy X-rays. This star defied regular explanations, orbiting an invisible companion, until it was shown to be in a gravitational relationship with a massive black hole. Cygnus X1. The discovery of Cygnus X1 provided clear proof in support of the presence of black holes and marked the beginning of a new research period into these cosmic mysteries. Cygnus X1, approximately 6,000 light-years away from Earth, has staggering properties. It is incredibly dense and exerts a force of gravity so strong that not even light can escape its grasp. This characteristic gave it its name, black hole, which encapsulates the entirety of these mysterious objects. Subsequent research has uncovered a variety of black holes scattered throughout the universe, with estimates suggesting that the Milky Way alone may harbor more than 100 million black holes, in spite of their elusive nature, which makes direct detection challenging. Astronomers have identified a number of candidates in our galaxy, with stellar masses ranging from black holes formed from the remnants of massive stars to supermassive black holes located at the centers of galaxies. The gravitational effect of black holes extends far beyond their immediate surroundings, influencing the evolution of cosmic structures and the outcomes of surrounding matter. Objects that get too close to a black hole have their fate decided by its unrelenting power. They are depicted as being drawn inevitably toward the event horizon, the final boundary, where they are subjected to powerful tidal forces and ultimately consumed by the black hole's singular core. This catastrophic interaction, known as spaghettification, is the extreme manifestation of a black hole's gravitational force. As an object gets closer to the event horizon, the gravitational gradient across its length becomes so extreme that it is stretched and twisted into a filament-like shape resembling spaghetti strands. The forces from the black hole overcome the internal ties that hold the object intact, causing it to disintegrate into a stream of matter that eventually merges with the TOD. Singularity. Despite the allure of black holes as testing grounds for the limits of physical theory, they remain cloaked in mystery. The quest to unravel their secrets continues, driven by a desire to understand the basic characteristics of space-time and gravity itself. In the expanse of the universe, black holes remain mute sentinels beckoning humanity to explore the depths of the unknown and expand the limits of human knowledge. Despite the immense distance from the nearest black hole, roughly 1,500 light-years away, questions and concerns regarding their potential consequences persist. In 2021, researchers achieved a significant advance by capturing the first clear image of a black hole, specifically M87, located at the center of the M87 galaxy. This remarkable achievement provided important information about the nature and elusive structure of black holes. The visual data revealed that black holes have complex layers, challenging the conventional wisdom of them as distinct, pure entities of nothingness. Through careful investigation and stitching images, scientists uncovered 3 distinct layers inside a black hole. At the outermost layer lies the crucial event horizon, the boundary marking the point of no return. Once an object crosses this threshold, gravitational forces become insurmountable, ensuring its inevitable descent into the depths of the black hole. Moving inward, the photon sphere constitutes the second layer, where light orbits the black hole in perpetual captivity. Any photons that make their way into this area succumb to the overwhelming gravitational pull, trapped forever within the cosmic embrace of the black hole. At the heart of the black hole lies the singularity, the third and final layer, where the laws of physics break down. The familiar laws governing the universe cease to apply, plunging researchers into a realm of extreme unpredictability and theoretical speculation. The difficulty of black holes and their inherent variation pose significant challenges to our comprehension. While they share a three-layer structure, every black hole demonstrates unique characteristics and behaviors, defying easy classification. As a result, traditional methods of scientific research are insufficient for studying these cosmic colossi, necessitating innovative methods for elucidating their mysteries. Indirect observation remains the most common method of studying black holes, as direct investigation is rendered unfeasible by the immense barriers posed by their gravitational forces. Attempts to conduct investigations would inevitably result in their devastation, unnoticed by the relentless forces at play. However, researchers continue in their quest to decipher the secrets of these colossal stars. Various theories ranging from the collapse of stars to cosmic dynamics offer tantalizing glimpses into their origins and behavior. Notably, NASA's study of the cosmic center of M87 revealed convincing proof of a supermassive black hole exerting its gravitational influence on vast cosmic scales. Despite these challenges, the pursuit of knowledge never ceases, motivated by the inherent curiosity of humans and a desire to comprehend. While the black hole mystery may defy simple comprehension, the steadfast dedication to scientific investigation promises to illuminate the gloomiest areas of the universe, deciphering the deepest secrets contained within. In 1963, Roy Kerr's groundbreaking work presented a paradigm-shifting perspective on black holes, proposing an innovative theory of rotating black holes that defied conventional understandings. Central to Kerr's model was the concept of the ergosphere, the area surrounding a black hole where opposing forces collide in equilibrium, preventing collapse by gravitational forces deeper inside. This novel domain displayed curious deviations from conventional physics, hinting at the profound mysteries concealed within dark matter. But the most intriguing implication of Kerr's theory was a prediction of an Einstein-Rosen bridge, more commonly referred to as a wormhole. This fictitious structure serves as a potential gateway through space-time, facilitating communication between distant regions of the universe or even parallel universes. The idea of wormholes stems from the complex interaction between Einstein's general relativity theory and the description of reality. In this way, structure and existence are intertwined, resulting in a known four-dimensional fabric, space-time. Massive objects warp this fabric, producing gravitational fields that influence the movement of surrounding matter. Wormholes, essentially, serve as shortcuts through this cosmic fabric, connecting far-off locations in space-time and possibly making it possible to move quickly over vast cosmological distances. However, the stability and practicality of wormholes remain subjects of intense speculation and debate among theoretical physicists. While the existence of wormholes offers tantalizing possibilities for interstellar travel and time exploration, significant challenges and limitations temper these prospects. Fantasies in my dreams. The fundamental wormhole instability, combined with the formidable barriers posed by quantum forces and radiation, casts doubt on their viability as practical methods of transportation. In addition, Einstein's theory of general relativity imposes fundamental limitations on how fast movement through virtual space can occur, implying that even if stable wormholes existed, they might not facilitate faster-than-light travel, a key component of many stories set in the future. In spite of these challenges, the allure of wormholes persists as an example of scientific curiosity and investigation. The concept of the wormhole, whose inventor is a scholar, embodies the tantalizing promise of cosmic portals and alternate realities. urging people to ponder the mysteries of the universe and contemplate the unending alternatives that lie beyond. The search for a single theory that unifies the gravity regions that appear to be spread out and the rise of quantum mechanics has led to a quest for a theory that covers everything, a comprehensive system that can incorporate all fundamental forces and particles throughout the universe. At the forefront of this endeavor stands Mayoku, a well-known theoretical physicist whose groundbreaking work has helped propel the study of superstring theory. Superstring theory represents a dramatic deviation from conventional models, hypothesizing that fundamental particles are not point-like entities but instead minuscule vibrating strings. These strings, much like a musical instrument's strings, resonate with particular frequencies, giving rise to the various particles and forces observed in nature. In this perspective, the universe becomes akin to a grand symphony, with each particle relating to a singular harmonic resonance of these fundamental strings. One of the most notable repercussions of superstring theory is its power to explain the enigmatic phenomena associated with black holes, wormholes, and other unusual solutions to Einstein's equations of gravity. As strings traverse the space-time fabric, their dynamic motion leads to the formation of gravitational singularities and topological anomalies. Nonetheless, the simplicity of superstring theory hides its inherent complexity, as it requires the existence of additional dimensions beyond the conventional 3 dimensions of space and 1 dimension of time. These additional dimensions, concealed from direct observation, pose a significant challenge to our instincts. Nevertheless, applied models, such as the analogy with fish living in a 2-dimensional lake, provide a glimpse into these higher dimensional realms. The compactification of these additional dimensions, like a paper rolled up in a fold, renders them imperceptible at everyday scales. But their influence permeates the fabric of reality itself. However, the specific nature of these concealed dimensions remains elusive, and a promising theoretical framework provides an explanation for the various intricate structures and universe-wide anomalies. In addition, the mathematical underpinnings of superstring theory have sparked a renaissance in mathematical physics, revealing deep connections between dynamic mathematical patterns and physical occurrences. Indeed, the pursuit of a complete theory has sparked the integration of disciplines, shedding light on the deep interplay between the natural and mathematical sciences. Despite its conceptual sophistication and potential for science, superstring theory remains an untested framework, awaiting validation. The elusive character of extra dimensions constitutes a formidable obstacle to experimental verification, relegating superstring theory to the realm of speculative mathematics. Nevertheless, the audacious vision of superstring theory continues to captivate the minds of enthusiasts and researchers alike, enticing humanity to embark on a journey of intellectual discovery and exploration. As we venture deeper into the known domains of theoretical physics with the help of the illuminating beacon of superstring theory, we confront the enormous enigmas of the universe, poised on the threshold of a new era of comprehension and enlightenment. The process of deciphering the secrets of quantum black holes has long perplexed physicists, representing a significant obstacle to our comprehension of the fundamentals of all things. Despite many efforts to solve this mystery, we still have no clear solution, prompting Edward Witten of the Institute for Advanced Study at Princeton to describe superstring theory as the physics of the 21st century that accidentally entered the 20th century. However, recent advancements have rekindled hope in the search for understanding quantum black holes. Several physicist groups have independently reported a substantial breakthrough, showing that string theory could provide a complete solution to the issue, though it lies within the more constrained context of 2 dimensions rather than the full 10-dimensional framework set forth by conventional superstring theory. While this is a promising first step, the search for a complete resolution is still in progress. The complexity of the situation presents significant challenges, and the quest for a unified theory of everything beckons us to look into the darkest corners of the universe's existence, where the lines separating reality and theory blur, and the secrets of the universe remain unexplored. The study of black holes carries profound repercussions for our comprehension of the universe, challenging our notions of reality and raising questions about the nature of the universe as a whole. The interplay between black holes and other astronomical phenomena, such as neutron stars and gamma ray bursts, reveals the intricate processes operating in the cosmos.